Hello everyone, today we'll be seeing about diodes. So let's go on with the introduction of them. A diode is actually a two electrode or a two terminal device that is made up of semiconductors. It is a simple PN junction with connecting leads on each side. So a diode is a one-way device, that is, it allows the current flow only in one direction or unidirectional. And the forward biasing of this diodes, that is allowing the current to flow through it with low resistance. It acts as a closed switch, and when you go for the reverse bias of this diode, the current flow is not allowed in it. That is, the current flow is restricted, and it acts as an open switch. So let's go on and see what this PN junction and how this forward biasing will affect it. So this is the PN junction that we were speaking about. This is the P-type region, and this is the N-type region. And what you see in between these is the depletion region. That is through which the electron and hole pairs generated in both the regions will start moving through them when you connect the uh, leads with positive and negative charges of the battery. So when you connect the positive end to the P region and the negative end for the N-type region, the current will start flowing through it. That is the forward biased condition, and the current will flow in the direction of positive to negative. And when you reverse bias it, that is, you'll connect the negative region over here to the p-type end and the positive to the n-type. This way the diode will be reverse biased and there is no current flowing through them. So let's go on for the circuit diagram of the diodes. This is the circuit diagram for a diode. Over here what you see is the p-type region, the arrowhead, and the bar represents the n-type end, and these two are the connecting leads. So when you connect it with the positive and negative, they'll act as the uh, forward biased, and the arrowhead that over here, which is the p-type end, the whichever side it's facing to, that will show the direction of the current flow also. This is also called as the cathode, and this one is the anode. Let's see the circuit completion of this. So this is the for circuit completion or circuit diagram completely for the forward bias condition where the positive end is connected to the p type and negative end to the n type, and the current will flow in this direction. So you can see that. So this is how the current will flow, and it will be the opposite for the reverse bias condition, and there will be no current flow. Let's go on further with it. And this is what is given over here also, that the approximately constant voltage drop occurs across a forward bias diode, and this simplifies diode circuit analysis. And whatever the diagram or the picture you're seeing over here, this is how the diode will really look. The uses of the diode can be of two types. That is, you can use it uh, in a transistor or a rectifier. These are few examples of it actually. They can be used in many other fields also. That is like for LEDs and etc. So as a rectifier and transistor, we'll be seeing that in the further videos. Let's go on further with this now. Uh, okay, here you can see that the diode can be used as a switch on, that is on when forward biased, and reverse biased it is off. And the PN junction provided with the copper wire connecting leads becomes an electronic device known as diode. So when you connect the PN junction along with the connecting leads in two ends, that is called the diode. And let's go on further with this. The P side of the diode is always the positive terminal for forward biased and is termed the anode. The N side, called the cathode, is the negative terminal when the device is forward biased. This is the PN junction that I showed before, and this one is the circuit diagram for it. I mean the circuit symbol, where the current is flowing in the direction of positive to negative or in the same direction as this arrowhead is pointing, with P type being the anode and N type being the cathode. And there are three types of these diodes, that is the low current, medium current, and high current diodes. So the low current diode is the one that you're seeing over here, which is shown as a small picture over here. And this black mark that you can see, that is the cathode end. This represents the cathode end, and the other one represents the anode. You can verify or find out the same thing with medium and high current diodes also, as mentioned in this image. Going on further with it, these are a few parameters that you should remember before you head further. That is VF forward voltage, IR reverse saturation current or the reverse current, and VBR reverse breakdown voltage, RD dynamic resistance, and maximum forward voltage or maximum forward current IF. And let's go on with the characteristics and parameters. Forward and reverse characteristics. The diodes can be made up of many materials. So we'll see about two of them, silicon diode and germanium diode. For a silicon diode, the forward and reverse characteristics, we'll be looking at it. And this is the graph related to the silicon diode, where you can see both the forward and reverse characteristics mentioned in it. So when you forward bias the silicon diode, the current flowing through it, that is over here, you can see it. This is the current that is shown in the Y region, Y axis, and then voltage is shown in the X axis. So even with too much of increase of forward voltage, there's not much increase in the forward current, and that only happens until 0.7 volts. Once you reach a 0.7 volt forward voltage, then after crossing that barrier, there is a linear increase in the flow of current. That is, the current increases very much even for a less amount of forward voltage increase after the 0.7 volts. And this is called as a forward voltage or VF of silicon diode, that is 0.7 volts. And let's go on with the reverse characteristics. This whatever we discussed before was the forward characteristics. Now going with the reverse characteristics, here you can see that the x-axis is actually having the nanoampere markings for the current, where in the forward characteristics you had milliamperes. So you can know that the amount of current flowing in the reverse characteristics for the silicon diode is too less. And as we saw it before, there is no much current flow for reverse bias condition. The reason is that the diode will not allow any current to flow through it. So you've seen it over here that when it is reverse biased, there won't be any current flow because when the reverse bias, the electrons in this region will start moving to the negative end, and the holes over here will start moving to the positive end, and the depletion region between these two will start increasing. That is, this gap over here will increase widely. So there's no chance of any contact or moving of these two holes and electron pairs with each other. Hence, there is no flow of current. But still, you over here you can see that there is some current that is shown over here. And this is because of the leakage of current that is happening in the diode. That leakage causes a little bit of current flow in it. After a few voltages, that is after some time when you increase the voltage step by step, when you reach the 75 voltage point, the current starts to increase drastically or linearly. And this is what we have for the silicon diode. Let's go for the germanium diode now. Germanium diode is also just like the silicon diode, but only difference over here is that the forward voltage for the germanium diode is 0.3 volts. That is, until 0.3 volts, you'll have the current increasing very less. Once it reaches the 0.3 volt point, the current will start increasing linearly, just like this silicon diode. And over here also you can see that the reverse breakdown voltage and the current produced in the reverse characteristics or for the reverse biasing is too less, because the current over here is only produced by the leakage of the electrons that is happening. Over here you can also see that the reverse breakdown voltage is 50 volts, but in the in silicon diode it was 75 volts. Even this is less. So hence we also prefer silicon diode more than the germanium diode for many of our uses. Let's now go for types of diodes, that is the ideal diode that we're speaking about. An ideal diode is actually the one which is not realistic, or you can say that they cannot exist in real, because for the ideal diodes, the forward voltage or the forward current that is produced at 0.7 volts or 0.3 volts for as that of the silicon and germanium is very high. That is, it is infinity. There is no resistance at all in it. So let's see that. So this is for the silicon diode over here. I mean the germanium diode over here, where the forward voltage is 0.3 volts. And for the silicon diode, it is 0.7 volts. In the image, we saw that the current was actually increasing up to here a little bit, and then it increased in a slanting way. But over here, you can see that there's no increase in the current up to here, and then it drastically increases or linearly increases completely. That is, there is no resistance at all over here. But when you see for the reverse characteristics, it will start going through the x-axis only. There is no current at all flowing in it. It only has a resistance or infinite resistance for both the diodes. So this is what is an ideal diode. That's it for this video. We'll see about the next concepts or remaining topics of diodes in the upcoming videos. Thank you.